Okay, so we've been calculating so far the, uh, the applying an external load and then calculating the internal moment. Well, let's calculate the external load that a person can handle if with their maximum muscle forces that are available. So we used PCSA to look at the available force in the biceps, the brachialis, and the brachioradialis. And we said that 8.2 centimeters squared equaled about 475.6 newtons for the biceps brachii. So we're going to say that's FBB. And then we said that 3.9 centimeters squared was proportional to about 226 newtons for the force in the brachioradialis. Then we said that about 14.4 centimeters squared was proportional to 835.2 newtons for the brachialis. So let's see, what would be the, how much would be the amount that this person could lift? So F of L, given these kind of maximum torques from our PCSA estimates. So let's look at an elbow angle of 60 degrees. So we're going to put here our free body diagram 60. And then we have essentially this here is F of L. It's acting downward. And that we don't know. But what we do know is that there's three muscles essentially here, these flexors, all acting on this forearm segment. So we have the force in the brachialis, we have the force in the biceps brachii, and we have the force in the brachioradialis. And they're all acting at different angles. So we'll call this one phi, this one theta, and this one alpha. So we'll just go up here and we'll say theta equals 85, and the brachialis is phi, that's going to equal 65, and then the brachioradialis is alpha, and that's going to equal 20. So we have all of our angles there. So let's put moment arms in now. Okay, and we're going to do, because we're going to solve this by decomposing the forces, we have to put our moment arms perpendicular to the segment. So they'll be perpendicular to the rotary component of these different forces. So we're going to put these lines in like this, so they're all perpendicular to the segment. Okay, then we can put distances in. So here we're going to say this is 3 centimeters. And then to the biceps, it's 5 centimeters. And then to the brachioradialis, it's 20 centimeters. And then to the external load, it's 30 centimeters. Okay. So now we just need a couple more things. We need to know like the angle here. So basically this angle is 60 degrees from the vertical here. So this angle here is also 60. Okay. And so there's the moment caused by the external load is only proportional to the rotary force because of the way we're calculating it. Approach we're using IM equals internal moment equals the external moment, and we're using the perpendicular forces. So we'll put this coordinate system there. Okay, so let's go ahead and start calculating some stuff out. So So our general equation looks something like this. So we've got FB perpendicular, so we'll do IM first, times at the moment arm FB plus we've got FBB perpendicular times the moment arm of the biceps plus FBR perpendicular times the moment arm of BR, and that's going to all be equal to F of L perpendicular times the moment arm. Okay, so we've got some work to do here. So basically, let's kind of work this out. So the perpendicular, FB perpendicular is going to be this part of the curve of the triangle. So we know it's going to be FB sine phi, and then that's going to be the same for the biceps and the brachioradialis. It's going to be F biceps brachii sine 85, F brachioradialis sine 20, and that's going to give us our different solutions. So let's write those out here. FBB perpendicular equals FB sine 85, FBR perpendicular equals FBR sine 20, and then FB perpendicular equals FB sine 65. Okay, so let's start plugging everything into this equation. So we need the perpendicular force times the moment arm. So we got 835 here times sine 65 times 3 centimeters is the moment arm. So let's do 835.2 sine 65 times 3 plus, so we've got biceps brachii, should be a B here. So we've got the perpendicular here. Okay, there's our equation. Here's our peak force output. So 475.6 sine 85, which is nearly 1. Okay, times its moment arm, which is 5. So we got that. Boom, boom. Here, now the moment arm there. So that's 5 plus. Okay, so this is done. So brachioradialis, then we've got 226 is its maximum. So we have sine 20, and then its moment arm is 20. And all of that's going to equal FL perpendicular times the moment arm of the load. Okay, and so we didn't really calculate the component of the load yet, and so basically what we have to understand is that this part is also going to be affected. So we'll put FL perpendicular here. It's going to equal to get this angle, it would be FL sine 60. Okay, so we have FL sine 60, and so then we would write this out as FL sine 60 and then times 30. So if we look at all of these together and we calculate the internal moments that are being generated, this is going to tally to 6,185.7 newtons per centimeter. And then if we divide by 100, that would give us 61.9 newtons per meter. Okay. Okay, so now what we need to do is like divide. So let's write this out over here. So we have 61.9 Newton meters. So we have to convert this, move these over to the left. So basically, let's go sine 60, and now this was in centimeters, and we're calculating this in meters. So we have to convert the 30 centimeters to meters. So let's divide that by 100 and put 0.3 down here. Okay, and then move it over to the left-hand side. So we're going to cancel this out, and then put over here sine 60 divide times 0.3, and that's going to end up giving us our answer. So it's going to be F of L equals 238.1 newtons. Those of you who still think in pounds, it's about 4.4 newtons per pound. So if we divide this by 4.4, we get around 54 pounds. Okay, or if you're working out at the gym in kilograms, we would divide the 200. We want to calculate this in kilograms. We would divide the 238 newtons by approximately 10, and we would get 9.81, and we would get the about 24 kilograms. So although clearly some of you can lift more than this gives us a general approximation of what people's capacity is who are in average shape.